Hello everybody, this video is going to be about what we call Vesper and the three-dimensional shape, the geometry of molecules. Up to this point we've been drawing Lewis structures which show you which atoms are connected and it shows you how many valence electrons each atom has, but they're not very good at showing you the three-dimensional shape. So that's where this thing called Vesper comes in. I do just like to preface this by saying that some people's brains have a lot easier time with the three-dimensional shapes than other people's. I have a very hard time visualizing this. I'm not very good at visualizing 3D in my head and turning these shapes around. So the nice thing is you can always look at printed pictures of the three-dimensional shapes. You can find online simulations where you can move the molecules around to help you visualize it. So there's definitely things you can do if you have a hard time with the 3D shape. And then you can just memorize it as well, right? There will be a little bit of memorizing some of the names for the shapes and the angles between the bonds, things like that. All right, so Vesper stands for valence shell electron pair repulsion. So you can see why we abbreviate it and just call it Vesper. So the concept here is that for the most part, the molecule is going to take a three-dimensional shape that's going to minimize all of the electron repulsions. Remember that electrons are negatively charged, and you do not want to have a bunch of negatively charged objects squished really close together. So the atoms will spread themselves out so that we end up with as little repulsions happening, as little interaction happening between the electrons as possible. So for example, here's just a little cartoon picture. If we have a center atom here and we have some bonds going on, but the bond between these two atoms, right, is holding them together. But there's also interactions between the electrons themselves. So it's these interactions that we're trying to spread out and trying to minimize. So let's just look at some of these shapes. Okay, so one of the shapes we can have is called linear. When you have a linear molecule, it's going to have a 180-degree angle between these bonds. You can see this is really spread out. If we were to try to pull these closer together, we would be getting more repulsions, more interaction. So the reason they spread themselves far out here is to get as much distance between each other as possible. A lot of times you'll see pictures online using balloons like this. The reason for that is they do a good job kind of filling the space and kind of showing you why you can't squish them closer together. So you might see a lot, they show it in videos and pictures, these balloons. Here's one called trigonal planar. This one is flat, and then the atoms spread themselves out almost like in a triangle, and that's going to result in 120 degrees between those bonds. And if you look at your balloon picture, you can see kind of it takes this triangle shape as well. The next one is tetrahedral geometry. This is such a good example of when the Lewis structure looks very, very different than the actual 3D Vesper structure. So a tetrahedron, I don't know if you took geometry, right, you would be familiar with this shape. So the base of this little pyramid is like a triangle. So we would have one atom on each of these corners. Each of these vertices would have an atom present. Well, if we were to draw CH4 as a Lewis structure, you put kind of one on top, one on each side, and one on the bottom, and it implies incorrectly that it's flat, like a pancake. It's not. You can see here we end up with one hydrogen on the top, and then the others spread themselves out in this triangle pattern towards the bottom. And what that results in is all of these angles between each one ends up being 109.5. So it minimizes the repulsions and it maximizes that bond angle as the best it can. So this is called tetrahedral. The next is trigonal bipyramidal. Okay, so when I look at this shape, if you look right in the middle here, right in there, do you see that triangle shape between these three chlorines? And if you imagine you have a top and a bottom chlorine, it's almost like you have two pyramids stacked on top of each other, right? And the base of the pyramid right here in the middle is a triangle. So trigonal bipyramidal is telling you that you have a triangle-shaped base and you have two of these pyramids kind of stacked together. This is the top of one, this is the top of the other, and they share the base right in the middle. So the ones on the top and the bottom we call axial, and the ones that are forming this middle triangle in here, this flat triangle area, we call those equatorial. Okay? The bond angle here between the axial and the equatorial is 90 degrees. And then between these equatorials ends up 120. So you end up with two different bond angles, but they are basically as spread out as possible. If we tried to make any of those bigger, somewhere else they would start getting smaller, right? And so this is as spread out as possible. The next is octahedral. So if you look at this one, instead of a triangle in the middle here, we have four. We have like a square, right? So we have four equatorials, and like before we have one on top, one on the bottom axial, if you're looking at it this shape. The thing that's a bit different here is that everything is 90 degrees. So you see these a lot when we have these expanded octets, right? If we want to look at octahedral with the balloons, you can start to see, right, this starts getting pretty crowded, doesn't it? We've kind of squished in our 6 balloons as much as we really can. And then I like this picture here because it kind of shows you these two these two pyramids, right? But instead of a triangle base, they have a square base in here. Okay. So when we have lone pairs, we have a bit of a problem because a lone pair is going to take up a little bit more space than a normal atom would. And so that's going to change the bond angles a little bit. It's going to cause them to get squished because that lone pair is going to squeeze them down and take up a little more elbow room. It pushes them out of the way. So what we say is that the lone pairs distort the shape. So if it normally had bond angles of 90, maybe it has a little bit less than that now, right? So the lowest amount of repulsions, we'll kind of go from small to big. If we have a bonded pair of electrons compared to another bonded pair, that's a smaller amount of repulsions than if you start adding lone pairs. If you have a lone pair and you have electrons inside a bond, there will be a little bit more repulsions happening. And then if you have two lone pairs, you're going to get even more repulsions happening. So let's look at an example of the bond angles getting distorted. So here we have tetrahedral geometry. We have 4 things bonded. But if one of those 4 things is a lone pair, rather than a true bonded atom, instead of having 109.5 degrees here, it's going to get squeezed down to 107 because the repulsion between that lone pair is going to be a little bit extra than you would expect. So we end up with a distortion. Here's another example, but this time instead of one lone pair, we have two lone pairs. So even though water, in theory, right, should have 4 items bonded, we have the lone pairs, we have 2 hydrogens, you would think it would be tetrahedral. It is tetrahedral, but it's a little bit distorted. Because 2 of those objects on that oxygen are lone pairs, it squeezes these atoms down, and this bond here ends up a little bit smaller than you would expect, because the lone pair is trying to take up some extra space. All right, next we're going to look at something that also contributes to the real shape, and that's something called hybridization. We don't go into this in depth. This is something you would learn a little bit more about in college chemistry, but we do give you a little bit of an overview so that it kind of helps you explain how we start getting these shapes that we get. So hybridization is when you blend 2 or more things together. So, now with all these designer dogs, right? Like if you had a poodle and a Labrador and they had a, puppy, you would end up calling it a Labradoodle. And it would be, not a full poodle, it's not a Labrador, it's somewhere in between. And so hybridization is what's going to happen when we take 2 or more orbitals and we kind of merge them together and we get something a little bit different, something that's in between the 2. Remember, we have s orbitals, we have p orbitals, we have d orbitals, we have f orbitals, and they all have different shapes. So we're going to be combining those different shapes to make new hybridized orbitals. So let's look at an example. If you have an s orbital and a p orbital, and you want these atoms to bond with each other, what's going to happen is instead of having, these 2 totally separate, different shaped orbitals, they're going to kind of merge together and form 2 of these strange hybrid orbitals. It's not an s orbital anymore. It's not a full p orbital anymore. It's somewhere strangely in between. And so you end up bonding. The electrons are going to move back and forth inside these hybrid orbitals, and that's going to result when they, are finished hybridizing, you get this 180-degree bond, right? So it's how we get the electrons to, instead of existing only in the s or only in the p, right? Now they kind of overlap those orbitals into something new, and we get a resulting shape, right? We get this 180-degree shape. Hybridization gets pretty weird because you start combining different numbers of orbitals, okay? So I'm going to show this to you on an energy diagram, right? And I'm going to show kind of like an orbital diagram. I'm going to show you how this ends up working. So normally we have an s orbital down here, and we have these 3 p orbitals, right? We have px, py, and pz. Well, if I make an sp hybrid, I'm going to take this s orbital, merge it together with one of the p orbitals, and I make this brand new set of sp shape. I have 2 of the normal p orbitals left, but now I have 2 of these new hybrid orbitals. And if you notice, the energy level is a little bit in between where they were originally, right? The s orbital was down here, the p orbitals are up here, and the sp ends up somewhere in between. It's like merging together, it's like compromising a little bit, right? So down here, you can see that we're going to merge these. I get my hybrids out, and then I have the leftover p orbitals that I didn't bother. I didn't change them. they're still unhybridized. They're still normal. Okay. The next type of hybrid is sp2. So hopefully you can kind of guess that that means we're going to have one s orbital combining with two of the p orbitals. So here's an s orbital. This time it's going to combine with two of the p orbitals. We have one p orbital left alone that we didn't mess with, and now we have these nice three hybridized orbitals that can now actually bond with each other because they're the same shapes, right? The next one is sp3. So hopefully this time you can guess that we're going to bond, or we're going to hybridize one s orbital and three p orbitals. And now if you look, we've combined all of these. There are no normal p orbitals left, are there? They've all been hybridized. So now instead of having two very differently shaped things, they all kind of exist somewhere in between. They can now bond. They result in the 3D shapes that we get. One thing that's a little strange is that they nowadays don't think that D and F orbitals hybridize like they used to think. So even just a few years ago, we would teach you D hybridization, and now we're kind of phasing that out because they don't really think that it actually hybridizes. So you're going to see D hybridization on like your VSPER chart, where you're looking at a big chart and it tells you all the different shapes you can get. But just realize that that may or may not be accurate. I'm curious in another 5-10 years kind of where that ends up landing. Do I take it all the way out? Do we, put it all back in? Do we have something like in between? I don't know. Okay. Now, one of the things I like about VSPER stuff is that you can find a lot of very helpful charts that can help you memorize the different shapes and the different hybridizations and things like that. One of the things you might see on the charts is something called the axe method. I really like this as somebody who struggles to visualize the three-dimensional shapes, because this is something that my brain can easily latch onto, and it helps me memorize it because it kind of presents me with like a little formula to follow. And so my brain is just more inclined to do well with that. So the axe method, we're going to use A to represent the central atom. X is going to represent how many bonded atoms you have. And E is going to represent the number of lone pairs on the central atom. Not all together, just the one on the center, because that's the one that will really decide the shape. Okay? So imagine, water in your head. Okay? If we have water, oxygen is our A, right? So we have A. We have two hydrogens, so we would have X2 because we have two X's. And we would have E2 because we had two lone pairs. Okay? Sometimes to make the charts work even nicer, what they'll do is you'll add these numbers together, the E and the X, and that will give you a steric number. So you can count how many objects are on the center atom, lone pairs and bonded atoms. That helps you find your steric number, and that helps you find the row on the chart that you want to look at. So the axe method is a way of just organizing this information for people. So for example, if you have something that's linear, like say, like carbon dioxide, right? Well, carbon dioxide, carbon is the A for our center. We have two oxygens that are bonded, and there's no lone pairs on carbon. So the axe formula for carbon dioxide would be AX2. And then I look across my chart, I find out it's linear, and it's going to be hybridized as sp. In order for the A atom and then X to bond with each other, they're going to take an s orbital and a p orbital, merge them together, and that's going to allow the electrons to form a bond inside that new formed orbital. Okay, so you can kind of see, like, we can get the same shape with different combinations. Like, you may have 3 bonded atoms, or you may have 2 bonded atoms in a lone pair, but you still have 3 items attached to the A, right? So that kind of helps you realize that, you know, even if you have different elements, different combos of like elements versus lone pairs, you can still get the same shapes and you can still get the same hybridizations. Everybody has different charts that they prefer. You know, if you find a VSPER chart that you really like, awesome. Go ahead and use it, right? I provide you with some that I really like in the reference section of your binder. If you hate mine, don't use it. Find your own. If you find one that you think is awesome, then send it to me, right? I'll throw it in the binder for next year. I'll put it up on the website, right? So, you know, if you find something great, please always share it. That's how I find a lot of good resources, okay? So here's a picture, just a little screenshot of one of the VSPER charts I like. This is probably my favorite because it's kind of all right in one place. So the electron groups right here, that's your steric number, right? How many things are attached. It shows you how many bonded groups you have and how many lone pairs. So if I were you, above this first column, I would write steric number. Then I would, over this column, write X. And over the lone pair column, I would write E. That will help you do your X formula if you like that. Okay. We have the electron geometry, which is kind of like a bigger, broader category. Those are helpful to know. I don't expect you to necessarily memorize the electron geometry, but you do need to know the molecular geometries. So I would put a star up above the molecular geometry one. You notice that the bond angle column says approximate, because remember, they may be distorted. So if it does end up bent a little bit, distorted a little bit, you know it's going to be a slightly smaller angle, like we learned with water, right? It's not 109.5, it's a little bit smaller than that. And then it uses the ball and stick models to try to show you some examples. And I think they did a pretty good job with arranging these to help you visualize that 3D shape. Here's the second page of the same chart. If you have a steric number of 5, these are the different combinations of X and E that you can get. It leads you to different shapes, bond angles, shows you the little 3D structures. This has all of them. We didn't go over every single one already in the PowerPoint. Just giving you a little bit of an idea in the PowerPoint. The chart will have all of the examples. This feels like a lot to memorize, but one of the things you'll notice is that once you get a feel for what they look like 3-dimensionally, like if you see something that's nice and flat in a triangle, your brain's going to memorize real quick. It's a trigonal planar, right? Trigonal, triangle, planar, flat, right? Water is bent. If I see something that looks like water, I know it's bent, right? If I see something that looks like CH4, I know it's tetrahedral. If I see something that looks like NH3, I know it's trigonal pyramidal. So if you start to kind of have your brain attach examples to different shapes, it will help you memorize it. Here's another one that a lot of kids like. It is a little bit blurry. It's one of those things that, it's been used so many times and scanned so many times. It's not super crisp anymore. Here's the steric number, and this time it only has the molecular geometries. Some people like this kind of chart set up where they can see, kind of go and see like these are, if I have no lone pairs. If I have a lone pair, these are my options. If I have 2 lone pairs, these are my options. So it doesn't matter to me which one you think is more helpful. Do a homework and look at both, and by the end of a worksheet or 2, you'll probably notice you're gravitating towards one chart more than another. One thing people always ask on this chart though is why are some of these lines, why are some of these like dashed triangles, and why do some of these look like normal triangles? And it's trying to help you with the 3D structure. If it's a line, it means it lies flat on the paper. If it's a dashed line like this, a dashed triangle, it means it's going into the paper away from you. The normal triangle means it's coming out of the paper at you, almost like a 3D movie or something, right? Where it pops out of the screen. So they use that to help with the 3D shape. Okay. All right. So I know that feels like a lot. Feels like a lot to memorize. The best thing you can do is start drawing some structures, start practicing your axe formulas, start using your charts, and try to get as many examples coming across, your eyes as possible. And then we will have an activity where we use a 3D modeling program to help us see the 3D structures, okay? And then something else you can do is anytime you have Lewis structure practice, even if I don't ask you to, just do a little bit extra and try to write the name of the shape down, right? If I ask you to draw BF3, it's a Lewis structure. You draw your Lewis structure and then just next to it write trigonal planar, right? So just, anytime you come across a structure, just ask yourself like, hey, do I know what shape this is? What's the Vesper for that? What would that bond angle be? Okay. All right, everybody, that's it. I hope that was helpful. Bye.